Have you ever wondered what makes your phone, your computer, or even the lights in your room work? It's not magic, it's science. And well, a huge part of that science is about materials. Think about it for a second. Everything around us is made of stuff. In the world of electronics, we use very special kinds of stuff to control electricity. We can group these materials into three main families: conductors, insulators, and a super interesting group right in the middle called semiconductors. Understanding these materials is the first step to understanding all the cool technology we use every single day. They are the fundamental building blocks, the Legos of our modern world, and each one has a very specific job to do. Conductors, the electron superhighways. Now let's start with the go-getters, conductors. A conducting material is something that lets electricity flow through it very, very easily. Imagine a busy highway with no traffic jams. That's what a conductor is for tiny particles called electrons. Electrons can zip through conductors with almost no resistance. Why? Because the atoms in these materials have electrons that aren't held on very tightly, so they are free to move around. The most common examples are metals. Think about the copper wires inside the charging cable for your phone. Copper is an excellent conductor, which is why we use it to carry electrical power from the wall outlet right into your device's battery. Other great conductors include silver, gold, and aluminum. Silver is actually the best conductor of all, but it's much more expensive than copper, so we don't use it for everyday wiring. Gold is fantastic because it doesn't rust or corrode, which is why you'll find it coating the connectors on high-end audio or computer cables. It ensures a clean, reliable connection for years and years. Aluminum is lighter and cheaper than copper, so you often see it used in big, high-voltage power lines that stretch for miles across the country, bringing electricity to our homes and schools. These materials are the workhorses of the electrical world. So, to recap, conductors are materials that give electrons a path of least resistance. They are essential for moving electricity from one point to another. Without them, we wouldn't be able to power anything. Think of a simple light switch. When you flip it on, you are completing a circuit with a conducting wire, allowing electrons to flow from the power source through the wire to the light bulb and back again. This flow of electrons is what we call an electric current, and it's all thanks to the wonderful properties of conducting materials. They are the unsung heroes that make our electrical grid and all our gadgets possible. Dielectrics, the electrical roadblocks. Now, what about the opposite of a conductor? That's where insulators, also known as dielectric materials, come in. If conductors are superhighways for electrons, insulators are giant brick walls. These materials do not allow electricity to flow through them easily at all. The electrons in their atoms are held on very, very tightly and can't move around freely. This is an incredibly important job. Think about the plastic or rubber coating around that copper wire we talked about. That coating is an insulator. It keeps the electricity safely inside the wire and stops it from giving you a dangerous shock. It also prevents the wire from touching other things and causing a short circuit. You see dielectric materials everywhere. The glass and ceramic structures you see on power poles are insulators, keeping the high-voltage wires from touching the wooden or metal poles. The plastic case of your television remote is an insulator, protecting the delicate electronics inside. Even the air around us is a pretty good insulator. These materials are all about safety and control. They help us direct electricity exactly where we want it to go and nowhere else. Without them, using electricity would be incredibly messy and dangerous. They are the guardians of the electrical world, ensuring everything works safely and correctly. This brings us to the most fascinating group, semiconductors. As their name suggests, they are somewhere in between a conductor and an insulator. Sometimes they conduct electricity, and sometimes they don't. We can control their ability to conduct, which makes them unbelievably useful. The two most famous semiconductors are silicon and germanium. In its pure or intrinsic form, silicon doesn't conduct very well. But here's the cool part. We can add tiny amounts of other elements to it in a process called doping. This changes its properties and turns it into an extrinsic semiconductor. Doping is like adding a special ingredient to a recipe to change the flavor. By doping silicon, we can create two types. One type has extra electrons that are free to move, called N-type, and the other has holes where electrons are missing, called P-type. By putting these N-type and P-type materials together, we can build amazing things like diodes and transistors. A transistor is basically a tiny electronic switch or amplifier. Your computer's processor contains billions of these tiny transistors, all made from silicon. They switch on and off billions of times per second, allowing your computer to perform calculations and run programs. Silicon is the foundation of the entire digital revolution. It's really the brain material of modern electronics. How atoms stick together. So, what makes a material a conductor, an insulator, or a semiconductor? It all comes down to how their atoms are held together or bonded. There are three main types of chemical bonds. First, we have metallic bonds, which you find in, you guessed it, metals. In this bond, atoms share their outer electrons in a kind of sea that flows freely among all the atoms. This sea of electrons is why metals are such great conductors. Next are ionic bonds, where one atom gives an electron to another. This creates charged particles called ions, which are held together by electrical attraction, like tiny magnets. Table salt is a good example. These materials are typically insulators. Finally, there are covalent bonds, where atoms share electrons directly with their neighbors. They form a very strong, stable structure. Diamond, a great insulator, is a perfect example of covalent bonding. Silicon and germanium, our semiconductor friends, also use covalent bonds. However, their bonds aren't quite as strong as diamonds. This means that with a little bit of energy, like from heat or light, we can knock an electron loose, allowing it to move around and conduct a current. This unique property is what makes semiconductors so special and controllable. The type of bond determines everything. We can also explain these differences using something called energy bands. Think of these bands as different energy levels that electrons can have inside a material. In a conductor, the energy bands overlap, so electrons can jump between them with no effort, allowing them to flow freely. In an insulator, there's a huge gap between the bands, called a band gap. It takes a massive amount of energy for an electron to jump this gap, which is why they don't conduct electricity. Semiconductors have a small, manageable band gap. A little bit of energy is enough to get electrons to jump the gap and start conducting. Now, how do we know if a semiconductor has extra electrons, which we call N-type, or extra holes, which is P-type? We can use something called the Hall effect. It sounds complicated, but the idea is simple. If you pass a current through a material and then apply a magnetic field at a right angle, the moving charge carriers, either electrons or holes, will get pushed to one side. This creates a tiny voltage across the material. By measuring which side the voltage appears on, we can tell whether the charge carriers are negative electrons or positive holes. It's a clever way to peek inside the material and see what's really going on. Magnets and more. Beyond conductors and semiconductors, there are other materials with amazing properties. Let's talk about magnetic materials. What makes a magnet a magnet? It's all about the electrons again. In most materials, the tiny magnetic fields of individual electrons are all pointing in random directions, so they cancel each other out. But in magnetic materials like iron, nickel, and cobalt, the atoms can align so that all their tiny magnetic fields point in the same direction. This creates one large, strong magnetic field. Think of a refrigerator magnet. It's made of a material where the atoms are all cooperating to create that magnetic force that sticks to your fridge door. We also have special purpose materials designed for very specific jobs. For example, superconductors are materials that, when cooled to very low temperatures, have absolutely zero electrical resistance. They are perfect conductors. They are used in powerful magnets for things like MRI machines in hospitals. Another special group is piezoelectric materials. These are crystals that generate a voltage when you squeeze or press on them. You might find them in the igniter of a gas grill. When you click it, you're squeezing a piezoelectric crystal to create a spark. Science is always discovering and creating new materials to solve new problems. Time for a quick quiz. Think you've got it? Let's test your knowledge with a few questions. Don't worry, it's not for a grade, it's for science. Read each question carefully and pick the best answer. This is a great way to make sure you've really understood how these amazing materials make our world work. Ready? Let's go. 1. Which of the following is the best electrical conductor? A. Rubber. B. Silicon. C. Silver. D. Glass. 2. The process of adding impurities to a pure semiconductor to change its properties is called A. Bonding. B. Doping. C. Insulating. D. Melting. 3. What type of chemical bond is found in metals, allowing electrons to move freely in a C? A. Ionic bond. B. Covalent bond. C. Hydrogen bond. D. Metallic bond. And just for your reference, the answers are 1 is C, 2 is B, and 3 is D.